Welcome, this is Professor Ridge. Today's lesson 3.7, Inverse Functions. And our first learning objective, verify inverse functions. Verifying that two functions are inverse functions. Inverse functions. For any one-to-one function, f of x is equal to y, a function f to the negative 1 power, and we read this as f inverse of x, is an inverse function of f if f inverse of y is equal to x. Okay, so let me make a little notation. So basically, you can think of it, if this is in our function, we have x, y, this is our function, and then our inverse function, we're going to switch the x and y. Okay, so if this is in our function, we had like 1, 3, the inverse function is going to, the input value would be 3 and the output value would be 1. So you're switching the input and output values. All right, this can also be written as f inverse of f of x is equal to x. So this is pretty much the idea that if you take an inverse function, well, first if you take a function, so you're going to input x into the function, you get y, then you take that output value and plug it into the inverse function. These basically, they're opposites of each other, so it's going to undo what you just did and get you back to where you started. That's kind of the way I think of it, right? So it gets you back to where you started. Okay, so this can be written as f inverse of f of x is equal to x for all x in the domain of f. It also follows that if you switch the order, you're going to put the input value into f inverse, take that output value and plug it into f, and again, these are going to undo each other, and you're just going to end up with what you started. Okay, so f inverse of x is equal to x for all x in the domain of f inverse if f inverse is in the inverse of f. The notation f to the negative 1 is read as f inverse, all right? Like any other function, we can use any variable name as the input for f inverse. So we will often write f inverse of x, which we read as f inverse of x. Keep in mind that f inverse of x is not equal to 1 over f of x, right? So this, in negative exponents, right, we know that negative exponents, if I was doing numbers, like 3 to the negative 1 power, that's equal to 1/3. But for function notation, this is not negative 1 power, it's f inverse, which is different than 1 divided by f of x. So if I wanted this one, I would have to write like f of x and say I'm taking that to the negative 1 power, and then that'll be this one. Okay, so that equals 1 over f of x, which is totally different than f inverse. And also note that not all functions have inverse. They left off the word. It should say inverse functions. Example 1, identifying an inverse function for a given input-output pair. If for a particular one-to-one function, f of 2 is 4 and f of 5 is 12, what are the corresponding input-output values for the inverse function? So remember what I was saying here. If this xy is in, so again, xy thinking of it as input-output, to get the inverse, you're going to switch them. So the output for f becomes the input for f inverse. And the input for f, the x, becomes the output for f inverse. So we're just going to switch the x and y coordinates. So if the input's 2, f inverse, that's going to become the output. That would be 2 over here, and the 4 is the output for f. So that's the input. Okay, and then for this one, same thing. So F inverse of, so 5 is the output, so we're going to switch it to the, I'm sorry, 5 is the input here, so for the inverse it would be the output. And then 12. Let me, I think a lot of students struggle with this notation too. If I put this, write this as a XY coordinate, remember the input, that's my X, this is my output, that's my Y. Okay, so F of X is a Y coordinate. F of X, this is a Y coordinate, right? So Y, which is equal to 4. So Y is equal to F of 2, which is equal to 4. Okay, so my X coordinate's 2, my Y coordinate's 4. So if I switch it for the inverse, it'd be 4, 2. Given two functions, f of x and g of x, test whether the functions are inverses of each other. So the technique is, first you determine whether f of g of x is equal to x, or g of f of x equal to x. If either statement is true, and then both are true, so basically you have to check both directions. If either statement is false, then both are false, and then these are, they're not inverses. Okay, so we have to testing the inverse relationship algebraically. So we're going to do the composition of f and g to see that we end up with x. So g of x is 1 over x minus 2, and we're going to take that output for g and plug it in to f. So then we get f of x is equal to 1 over, now we're going to take the x out. Okay, so we're going to take the x out and put in 1 over x plus 2. Oh, I'm sorry. This is f, 1 over x plus 2. So I put the x out, put a blank parenthesis. Now I'm going to plug in 1 over x minus 2 for the x in the f function, like this. Now with order operations, we can drop these parentheses because there's nothing out in front. And then the minus 2 and plus 2 make 0, and then 1 over x plus 0 is just 1 over x. And then 1 over x, you view this as division, and you're going to flip this 1 divided by 1 over x, then you're going to multiply by the reciprocal. Or you can view this as just saying the reciprocal of 1 over x, which is just x. Okay, so that works. So we can say that now we have to test both directions. Okay, so if we're going to test the other direction, so it'll be g of f of x. So g f of x is 1 over x plus 2. And then we're going to, g is the 1 over x. I'm going to put a blank parenthesis where the x is, minus 2. And I'm inputting the output for f, so which is 1 over x plus 2. So I'm going to put that where the x is. Okay, now this one's a little more difficult because I want it to, oh, actually no. Think of this as reciprocal. 1 over x plus 2, so the reciprocal of this would just be x plus 2. Or I can think of it this way, 1 divided by 1 over x plus 2, and then the way you divide a fraction is you multiply by the reciprocal, so x plus 2, and then the 1's can just go away because it's just 1, so then you get x plus 2. And then the plus 2 minus 2 cancel. We get x plus 0, which is just x. So it works, both directions work. So remember, we want to check that they undo each other and you just end up with x. Okay, which they do. So from a rule up here, since both of those are true, then we know G is equal to F inverse and F is equal to G inverse. So F and G are inverses of each other. So yes, G is equal to F inverse, and vice versa. F is equal to G inverse. Example 3, determining inverse relationships for power functions. If f of x is equal to x cubed, the cube function, then g of x is equal to 1 over 3 times x. Is g equal to f inverse? Alright, so we're going to try both directions. F of g of x, and that equals f of 1/3 x. So we take g of x out, put in the 1/3 x. Now we're going to put this in for x in the f function. The f function is x cubed. And if we simplify this, we got to use the power of a product rule, which is you're going to raise both of these to the third power. And then simplify that, you get 1 over 27x cubed, which is not equal to x. So we can just stop and say no, right? It has to work both directions. So if it doesn't work either, both directions, meaning f composed with g and then g composed with f. So the answer is no. G is not f inverse. Next learning objective, determine the domain and range of an inverse function and restrict the domain of a function to make it a one-to-one function. Finding the domain and range of inverse functions. So the outputs of the function f are the inputs of f inverse. So the range of f is also the domain of f inverse. Likewise, because the inputs to f are the outputs to f inverse, the domain of f is the range of f inverse. So if we go back to that first slide when I was talking about switching, right? So if you're going to do this for every x and y value, you're going to switch x and y, and then y becomes x. So the range for f becomes the domain for f inverse, and the domain for f is the range of f inverse. So you're going to switch all those x and y coordinates, which brings us to this picture, they can say. So we're switching, the a becomes, a is in the domain of f, but it's the range of f inverse, and b is in the range of f, so a goes to b, so input output. Now if we're going backwards, this would be the input, that would be the output. So this set of numbers would be the domain of f inverse, and this set of numbers would be the range of f inverse. So you're just switching them all. And basically we make that rule. The range of f of x is the domain of the inverse function f inverse of x. And the domain of f of x is the range of f inverse of x. Given a function, find the domain and range of its inverse. If the function is one-to-one, write the range of the original function as the domain of the inverse, and write the domain of the original function as the range of the inverse. Now, if the domain of the original function needs to be restricted to make it a one-to-one function, then this restricted domain becomes the range of the inverse function. Okay, so what we're talking about here is if you look at, let's say f of x is equal to x squared. So for instance, if I put in 2, I get an output of 4. But if I put in negative 2, I also get an output of 4, because negative 2 times negative 2 is 4. So if I want to do f inverse, and I switch this, the problem is if I switch this, this would be 4, 2, and then this would be 4, negative 2. So we have this repeated x value that has, remember from our arrow diagrams early on, we get 2 output values, so this is not a function. Okay, so we get 2 and negative 2, so it's not a function. But if we restrict the domain to be just x can only be, x has to be greater than or equal to 0 for our domain, then this is not in the function. And then when we do the inverse function, this one gets thrown out, so now there's only one answer. Okay? Example 4, finding the inverses of toolkit functions. Identify which of the toolkit functions besides the quadratic functions are not one-to-one, and find a restricted domain on which the function is one-to-one, if any. So the toolkit functions are reviewed in table 2 right here. So the constant function, that one is not one-to-one because it's a horizontal line, so basically every x value is going to have the same output value. So how would you restrict that? You can, the only way to restrict this one is you'd have to make it to be just one input value, one output value. So it's not really practical on that one. So there's no domain other than the single point. Identity function. The identity function, if you recall, the identity function looks like this, right? And it passes the horizontal line test and the vertical line test. Vertical line to be a function, horizontal line to be one-to-one. So that one's one-to-one. So this is one-to-one. Quadratic, this one is not one-to-one. So how do we restrict the domain? So if you think, again, if you think of the graph, it's going to be a parabola. So if we restrict the domain, like I just said, to be just the positive values, so for quadratic, we're going to restrict the domain to be x has to be greater than or equal to 0. And then the square root function is actually going to be the inverse of the quadratic. And then, let's see, cubic, that one, cubic is one-to-one. Cubic is one-to-one, passes horizontal, right? So that one's one-to-one. Reciprocal, if you remember the reciprocal function, looks like that. That one's one-to-one. Okay, the reciprocal squared, that one's not one-to-one because if you recall the graph of the reciprocal squared is something like this, where we get, and it's going to fail the vertical line tests. So again, typically you're going to restrict the domain to be just the positive side, but you could restrict it to the negative side. So the domain would be, if you're going to restrict the domain, it has to be x is greater than or equal to 0. So now the domain for the actual f of x is all real numbers except 0, right? But if we want to get the inverse function and to make it one-to-one, you have to restrict the domain to be greater than or equal to 0. Or you could actually do it the other way. Oh, 0 is not included in this one, so I need to throw out the equal to sign. Strictly greater than. Okay, cube root is 1-to-1, so no problem with that one. Square root is 1-to-1 because if you remember, the square root is going to be this function. So the domain is just from greater than or equal to 0, and it's actually the inverse of this quadratic if the quadratic's restricted as I wrote here. Okay, and then absolute value is not 1-to-1, so again you would have to restrict the domain to be either greater than or equal to 0 or less than or equal to 0, depending on what you want for your inverse function. So the absolute value, this one's not 1-to-1. This one was 1-to-1. Not 1-to-1. And then again, you'd have to restrict it to a single point. So typically we want to do that one. And then this one is not 1-to-1. So you're going to restrict it to either greater than 0 or less than 0, again, depending on what you want for your inverse function. And then this one, that's the v that we just talked about in last section. So again, it's going to fail the horizontal line test, so you restrict the domain to be either, this one you can be equal to 0, or you can do it less than 0. So basically all of them you can do that, depending on what you want for your inverse function. Okay, the next learning objective, find or evaluate the inverse of a function. Finding and evaluating inverse functions. Example 5, interpreting the inverse of a tabular function. A function f of t is given in table 3, showing distance in miles that a car has traveled in t minutes. Find and interpret f inverse of 70. So again, remember that if we're thinking of this table, if we're going this way, this is our f. F inverse will be going the opposite direction. This would be F inverse. Right? So the 70 in here, this is our input for F inverse, which is the output for F. So we're looking at, we want to find the output value for F, which is 70, and then it's going to give us, so F inverse of 70, I'm saying two different things, but they're the same, right? So if I think of it this way, this becomes this is my input output for F. I'm going to go backwards. This would be for F inverse, this would be my input, and this would be my output. So I'm going backwards kind of thing. So if I input 70 into F inverse, the output's going to be 90. So what we're saying here is that to drive 70 miles, it's going to take 90 minutes. So to drive 70 miles, it will take, that's the interpreting part, 90 minutes. Right? For F, if you drive for 90 minutes, then you have driven 70 miles, and this going backwards. If I've driven 70 miles, it took 90 minutes. Evaluating the inverse of a function given a graph of the original function. So the technique is, given the graph of a function, evaluate its inverse at specific points. So first, find the desired input on the y-axis, because remember, the input becomes the output, output becomes the input. then read the inverse function's output from the x-axis. Okay, so here's an example, evaluating function and its inverse from a graph at specific points. So a function g of x is given in the figure 5. Find g of 3. Okay, so g of 3. So our input is x, and g of x is the y value, the the output. So if I put input is 3, I go up to the graph. So see, that point is, that's for g. If x is 3, y is 1. Okay, so again, if you think of, I'm going to do, actually, yeah, g of 3. Let's do red. You go up to the graph, it hits there, and then you go over to the y-axis. So if the input is 3, the output's 1. Now, for g inverse of 3, we're saying, so if this is g, we want the output to be right. The input here for g inverse is going to be the output for g. So we got to go to where the y-axis for g is 3, go over to the graph, and then what's the x-coordinate to get me y equals 3? So remember, we're going backwards now. So that will give me, so for g, g of 5 is equal to 3. So g inverse of 3 is going to be 5. Right? And that's how you do it. Finding inverses of functions represented by formulas. So the technique, given a function represented by a formula, find the inverse. So first, make sure f is a one-to-one function. Solve for x. Interchange x and y, and then replace y with f inverse of x. Okay, variables may be different in different cases, but same idea, same principle. Okay, so find a formula for the inverse function that gives Fahrenheit temperatures as a function of Celsius. I actually do that a little different than the way it's stated here. I'm going to, okay, so we want to find a formula for the inverse function that gives Fahrenheit temperature as a function. We want Fahrenheit as a function of Celsius. So we want f all by itself over here. So we're going to rearrange this to get f all by itself. So let's see, if I multiply both sides by 9 over 5, the 9 over 5 and the 5 over 9 cancel each other. So those cancel. And then I can drop the parentheses, and then I can add 3 to both sides. Oh, that should be 32. 9/5 C equals f minus 32, and then add 32 to the other side. So then we get f equals 9/5 C plus 32. So our Fahrenheit written as a function of C would be 9/5 C plus 32. Oops. Okay, so then the book goes a little further to tie in this idea of inverse. So if the original function, if we call that h of f, this is the function to convert Fahrenheit to Celsius, is going to be 5/9 f minus 32, then the inverse function, and remember you're going to switch the C and F. So if we plug in Celsius to get Fahrenheit, be 9/5 C plus 32. So H and H, these are inverses of each other, just to kind of tie it in with the terminology up here. Example 8, solving to find an inverse function. Find the inverse function. F of x is equal to 2 over x minus 3 plus 4. So this is the way I do it. We're going to rewrite the f of x as y. So I think I'm going to do it a little different than the how-to. So right now my first step, I'm actually going to interchange the x and y right now. So all the x's become y's, all the y's become x's. So this will become x equals 2 over y minus 3. Okay, and then now I'm going to solve it for my new y. I think the way the book says just solve it for x and then switch the x and y. I like to switch it first, solve for the new y. Okay, so now solve for new y. So technically this is the inverse of the original function. But to write it as an inverse function, we want to get y by itself and then convert it to the function notation f inverse. Okay, so my first steps, I'm going to subtract 4. And then I'm going to, here's a shortcut for proportions that you should know. Oops. So if I have a fraction equals fraction, so I'm going to put this over 1 to make it a fraction. You can interchange the numerator and denominator across the equal sign. So I can put the y minus 3 up here and the x minus 4 down there. So I get y minus 3 over 1, which I don't need to write the over 1, 2 over x minus 4, and then I want to solve for y, then I'm going to add the 3. Now you can leave it like this. If you want to combine this and make it one fraction, you can. Since the original problem was written like this as a fraction plus a whole number, I'm going to go ahead and leave it. And now I'm going to write this f as f inverse. So then f inverse of x is this new y that was solved for y. So 2 over x minus 4 plus 3. And that will be my f inverse. Example 9, solving to find the inverse with radicals. Find the inverse of the function f of x is equal to 2 plus square root of x minus 4. So this is a one-to-one function, right? If you were to graph it, this is a square root function. You're going to shift it right 4 units and then up 2. So right 4 units, up 2, it's going to be something like this. Okay, so our domain is going to be, this is 4. So domain is going to be from 4 to infinity. And the range is going to be from 2 to infinity. Okay, and it's a one-to-one function. So let's see, now the inverse. So again, the way I do it, I'm going to write f of x as y. And then I'm going to do the inverse now. I'm going to switch the x and y, or interchange, however you want to say that. So all the x's become y's, all the y's become x's. So this is technically the inverse. Now to make it an inverse function, I want to make sure that I restrict the domain if I need to, which we already said is 1-to-1, so we don't have to worry about that. And I'm going to get the y by itself. So I want to subtract 2 from both sides. And then I'm going to square both sides. So x minus 2 squared equals y minus 4. And then I'm going to add 4 to both sides. So minus 2 squared plus 4 equals y. And then that's going to be f inverse. The y becomes f inverse of x. X minus 2. Now this is a parabola. If you're to graph this, this one's not a 1-to-1 function, but we got to remember that the domain's going to become the range, and the range is going to become the domain. So we have to restrict the domain for this one. The domain is from 2 to infinity. Okay, and then the range would be from 4 to infinity. All right, and if you were to graph this, it would be just the right half of the parabola. And hopefully, at some point you'll start learning all this. Don't get too stressed out about it right now. Okay, and our last learning objective for this lesson is use the graph of a 1-to-1 function to graph its inverse function on the same axis. Finding inverse functions and their graph. Now that we can find the inverse of a function, we will explore the graphs of functions and their inverses. Let us return to the quadratic function f of x equals x squared with a restricted domain 0 to infinity. So it's just the right half of the parabola, like I was mentioning in the example before, on which the function's 1-to-1. So see, it passes both the vertical and the vertical line test to be a function, and horizontal line to be 1-to-1. Okay, now restricting the domain 0 to infinity makes the function 1-to-1. And it passes the horizontal line test, which I just mentioned. So it has an inverse on this restricted domain. Now the way that you find the inverse, remember originally we were talking about if f has the point x, y in it, then f inverse is going to have y, comma, x. Right, so you're going to switch the x and y. Well, if we graph the line y equals x, which is just this diagonal, y equals x is 0, 0, 1, 1, 2, 2, 3, 3, so on. Oh, I should have made this graph bigger. Okay, so what we're going to do is so for instance, if I had the point 3, 1 on this graph, 3, 1, and I switch it, if I switch it, it'd be 1, 3. So 1, 3 would be here. And this is what you'll notice is this is what we call, it's reflected through the line y equals x. So it's the mirror image through the line y equals x. So what you can do is take each point that's on the blue graph here, let's make it red, so this 0, 0, when you reflect it, it stays at 0, 0. So any points that intersect the line y equals x is going to stay put. And then you can see if this point right here is like 1/2 0.25, then the reflection point is going to be over here. And then if this is at 2, 4, then it's going to be 4, 2. So I just had to extend that a little bit. So here we see this is like 1.42, so it'll be 2, 1.4. And then kind of if you had this on a piece of paper and you folded the paper on this line y equals x, the two halves would match up. So you kind of like think of the mirror image of that point, kind of like this. And then it goes out that way. So this is going to be f inverse of x. okay, which is the square root function. Okay, let's look at example 10, finding the inverse of a function using reflection about the identity line. Remember, the identity line is y equals x. So I just start out negative 6, negative 6, negative 5, right? So x and y are the same coordinates. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So that's our identity line, y equals x. And then I'm going to, so what I noticed that this has a vertical asymptote for the y-axis. So when I flip it over that line, it's going to have a horizontal asymptote, and it'll be the x-axis. So for instance, here this, and then just take points and flip them. So 0, 1. So if I flip it, it'd be 1, 0. And then this one looks like, well, actually, that wasn't quite 0, 1. It's off a little bit. This one's just about 2, 1. So let's see, 2, 2, 1. So I'm going to do 1, 2. And then this one looks like about 4, 2. So I'm going to do 2, 4, or just about. And then this is going like 1/2, 1/2, negative 1. So I flip it. It'll be negative 1, 1/2. And see how it's going to this y-axis. It's going to go to the x-axis. So this is like 0.13, negative 3. So negative 3.1. So basically, we want to draw having an asymptote on the y-axis or x-axis, and then this curve up like that. And if you flip if you fold the paper on that line, they should kind of match up. That's the mirror image through the line y equals x. And that's pretty much how you do it. Okay, and that brings us to the end of this lesson. And again, practice, practice, practice. Do as many of those odd exercises you can. And if you feel like you need more, do some of the even ones as well. All right. Have a good day, and I'll see you next time.